Okay, so this is going to be part 3 of our videos on chemical equilibrium. And I'm going to show you one more type of calculation here, and basically what happens when your simplifying assumptions fail. So we're going to go back to the reaction that we started with, the equilibrium between N2O4 and NO2. So let's suppose at some temperature, this has an equilibrium constant equal to 4.50. All right, so let's suppose 0.3 moles of N2O4 are placed into a 2-liter container, and we want to know the equilibrium concentration of both gases. Okay, so we're going to set up our ice table, initial change and equilibrium. So initially, how much N2O4 do we have? So this is a concentration term, and I gave you moles, right? So 0.3 moles divided by the volume of 2 liters gives us initial concentration of 0.150. The NO2 concentration is initially 0. This was not mentioned, so there's no NO2 to start with, right? So the reaction is going to shift to the right, because we start with all N2O4 and no NO2. So this will go up, this will go down, and this will go up until the ratio becomes equal to 4.5. So we'll use X, so we know the reaction is going to shift to the right, because we're not starting with any NO2. So we'll let X represent the amount by which it shifts. But this is not a 1-to-1 stoichiometry, okay? Lose 1 here makes 2 here, right? And that has to be reflected in the change. So if this goes down, we'll let X represent the amount by which this goes down, then this will go up by 2X. So that our equilibrium concentrations will be 0.150 minus X and then 2X. So our equilibrium constant will be equal to 2X squared, right? The coefficients become the exponent, so it's 2X squared divided by 0.150 minus X is equal to 4.50. And this is what we have to solve. And this time we can't make any simplifying assumptions. It's not a perfect square where we can take the square root of both sides, and it's not a small k where we can go in and neglect the effect of the dissociation. So the first step that I did here was to cross multiply. Okay, so 2x times, first of all, 2x times 2x is 4x squared, so that's simplified a little bit. And then I cross multiplied, right? So 4x, if you have 4x squared over 0.150 minus x is equal to 4.50 over 1. Anything divided by 1 is the number itself. So this times this is equal to this times this. That's what I did in the next step. So 4x squared is equal to 4.5 times 0.150 minus x. Okay. Then I distributed the 4.5. Okay, so 4.5 times 0.150 is 0.675. And obviously 4.50 times x is 4.50x. So 4x squared is equal to 0.675 minus 4.50x. And then I rearrange this and move the x and the 0.675 over to the other side so that we have 4x squared plus 4.50x minus 0.675 is equal to 0, right? And you probably know why I did that. I basically rearranged it into the form ax squared plus bx plus c is equal to 0. Basically, so that we can use the quadratic formula. Your solution is negative b plus or minus the square root of b squared minus 4ac, all of that divided by 2a. Okay, so a is 4, right? That's a. A is 4, and b is 4.50, and c is negative 0.675. So negative 4.50, that's negative a, or negative b rather, negative b plus or minus square root b squared 4.50 squared minus 4ac. A is 4, c is 0.675. All of that, basically this whole thing divided by 2 times 4, which is 8. So 4.50 squared is 20.25 plus 10.8. You take the square root of that, okay, and you get negative 4.5 plus or minus 5.57 divided by 8, and you come out with 2 possibilities for x. You always get 2 solutions to a quadratic because of the plus and minus, okay, 0.134 and negative 0.126, which you can discard, right, because you can't have a negative concentration. So NO2 comes out to be NO2. We set the problem up. NO2 is 2x, so that's 2 times 0.134 or 0.268 molar. Okay, and N2O4 is 0.150 minus x, or 0.150 minus 0.134, and that comes out to be 0.016 molar. So that's basically how you work a problem like this. This is mathematically this is as bad as it'll get, is basically having to solve a quadratic if you can't do any simplifying assumptions. All right. So there is one more thing that we need to talk about here. We'll wrap this chapter up, and that is Le Chatelier's principle. Okay, and Le Chatelier's principle says that if an outside influence disturbs an equilibrium, the system changes in the opposite direction to restore the equilibrium. So, in other words, if a system is at equilibrium and we upset that equilibrium in some way, in other words, we add a product, or we remove a product, or we add a reactant, or we remove a reactant, once we upset it, once we add something or take something out, it's no longer at equilibrium, and it's going to readjust itself until it is at equilibrium. Okay, remember, a reaction that's not at equilibrium will shift until it is. And that's basically Le Chatelier's principle. Okay, so what sorts of things can affect the position of an equilibrium? First of all, obviously, it should be obvious that if you add something or you take something out, it's going to upset the equilibrium. So the first is adding or removing products or reactants. Okay, so if you remove a product, it's going to shift to the right, because the products are on the right side of the equation. If we take out a product, the reaction is going to want to seek to replace what we've taken out. Well, how can it do that? By a shift to the right, right? If we have a simple reaction, A makes B. A in equilibrium with B, rather. Okay, so if we take if we remove B, okay, it's going to want to replace what we've taken out. How can it do that? By shifting to the right. So the A will go down and the B will go back up until the system is at equilibrium one more time. Okay. Now if we add a product, it's going to shift it the other way. If we add B, now this B is too big. So if we add B, that's going to shift the other way. B will be converted into A, or product will get converted into reactant. Okay. If we remove a reactant, it will shift it to the left. So if for some reason we were to take out some of the reactant A, again, it is no longer at equilibrium. It's going to seek to reestablish the equilibrium, so it's going to shift to the left. So removing a reactant will cause it to shift to the left. And then last, if we add a reactant, let's say we added A, then now A is too big, so again that's going to shift it back to the right. In other words, A would get converted into B. Okay. Now, if your reaction involves gases, another thing that we can do is you change the volume, basically, or change the pressure. Changing the volume has the effect of changing the pressure. Okay, so if the reaction has more gaseous reactants than products, increasing the pressure will shift to equilibrium towards more products. The classic example of this is the Haber process for the production of ammonia. In other words, 3 hydrogens plus nitrogen makes ammonia. Now look at this reaction carefully. You have 2 moles of gas on the right side, okay, and 4 moles of gas on the left side, okay. So if we change the volume, like I'm using volume, I know I'm using volume and pressure interchangeably. If we force it into let's say we force it into a smaller volume, that will increase the gas. That will increase the gas pressure. The pressure is going to go up. So the reaction, that's the stress on this reaction. How can the reaction seek to alleviate that stress? By shifting to the right. Okay, shifting to the right makes the pressure go down. Why? Because there's fewer moles of gas on the right. We have 4 moles of gas on the left and 2 moles of gas on the right. So if we stress the system, one more time, if we stress the system by forcing it into a smaller volume, we put it under pressure, okay, then it's going to shift to the right, because that alleviates the pressure. That helps to alleviate the pressure because we're reducing the number of moles of gas. So basically you could drive this reaction to the right by decreasing the volume, increasing the pressure, forcing it into a smaller container. Okay? Now of course the reverse is true. If a reaction has more gaseous products than reactants, increasing the pressure will shift it towards reactants. So we'll keep picking on this reaction between N2O4 and NO2. Okay, now the reverse is true. We have more moles of gas on the right side. We have 2 moles of gas here in the NO2 and only 1 mole of gas on the left side on the N2O4 side. So basically, if we increase the pressure or to decrease the volume, force it into a smaller container, it's going to shift towards the left. It's going to shift this way, because shifting to the left decreases the number of moles of gas. As NO2 gets converted into N2O4, the pressure will go down because you will have fewer moles of gas. Okay? And then last, a third case is if a reaction has equal moles of gaseous products and reactants, then of course increasing the pressure will have no effect. So for example, the reaction between H2 and I2 to make 2HI. Okay, we have 2 moles of gas on the left, 2 moles of gas on the right. Changes in pressure or volume will do nothing. Will do nothing to this reaction. And then last, this applies only to reactions that involve gases. Okay? Changes in pressure or volume have no influence on reactions that do not involve gases. Okay, so changes in pressure only influence gases. Okay. So next, changes in temperature. Okay, obviously, changing temperature often influences reaction rate, and if that's the case, then it's going to affect the position of the equilibrium. All right. So, which way it shifts is going to depend upon whether the reaction is endothermic or exothermic. Okay. Now, if the reaction is exothermic, heating will actually shift it towards reactants, and the cooling will shift it towards products. Now, let's think about this carefully. A reaction that's exothermic means it's giving off heat. In other words, we could think of heat as a product. So let's say we have, back to our simple reaction, let's say we have reactant A in equilibrium with product B. But let's say it's an exothermic reaction, then we can think of heat as a product. We could write heat over there on the reactant side. So in other words, by heating it up, we're essentially adding a product. And we know from the previous slide, if we add a product, we shift the equilibrium to the left. So if the reaction is exothermic, heating will actually shift it to the left. If you're actually interested in making the most product that you can, and the reaction is exothermic, then you want to cool it. Because cooling it will shift it towards the formation of products. Okay. Last, not almost last, not quite. If a reaction is endothermic, now the opposite is true. If the reaction is endothermic, now endothermic means it's taking in heat. Right? We could write an endothermic reaction like this, or we could the heat would simply be on the other side. Okay, so in an endothermic reaction, we could think of heat as a reactant. So if we heat it up, we're giving it a reactant, so heating will shift it towards the products. Cooling will shift it towards reactants. So in other words, we could write an endothermic reaction like this. And now heat is a reactant. So heating it will shift it. By adding heat, you're adding a reactant, and that shifts it towards products. Now last is the addition of a catalyst. Now a catalyst will change the rate at which the equilibrium is achieved, but it has no effect on the position of an equilibrium. So one more time, a catalyst causes a reaction to go faster, but if it's an equilibrium reaction, it won't change the position of the equilibrium. So it will change the rate at which the equilibrium is achieved. The reaction may go faster, but it will have no effect upon the position of the equilibrium. And that wraps up chemical equilibrium.